Welcome to Unit 2.2, which is called Redox, Rusting and Iron. Your specification for this topic is on page 1 and 2. Have a read through this to see what you can expect in this topic, what we're going to be covering in this topic. But in this first video, we're going to cover this idea of oxidation and reduction in terms of loss or gain of oxygen or hydrogen, and also in terms of electrons, which goes on to Unit 0.2.2.2. And we are going to look at what a redox reaction is as well. So we're going to cover these first 2 points of the specification in this video. So over on to page 2, we're going to introduce this idea of oxidation and reduction. So those are two really key terms, and we'll have a look at how we can define them in just a second. So oxidation and reduction. So really oxidation and reduction, we're going to define them in terms of the loss or gain of oxygen, hydrogen or electrons. It doesn't have to do all of these, it doesn't have to involve oxygen, hydrogen and electrons, but it has to involve one of them and the loss or gain of one of them. So we're going to have a look at what oxidation is in terms of oxygen, hydrogen and electrons, and we're going to have a look at what reduction is in terms of oxygen, hydrogen and electrons. So first of all, oxidation. So oxidation is the gain of oxygen. So in terms of oxygen, oxidation is the gain of oxygen, and that makes sense from the name of it. It's oxidation, it's gaining oxygen. But in terms of hydrogen, oxidation is the loss of hydrogen. So oxidation is the gain of oxygen or the loss of hydrogen. Finally, in terms of electrons, oxidation is the loss of electrons. So if something loses electrons, we say that it has been oxidized, it has undergone oxidation. So oxidation is the gain of oxygen, the loss of hydrogen and the loss of electrons. Essentially what we say with reduction is that it's the chemical opposite of oxidation. So it's the chemical opposite process of oxidation. So instead of oxidation being the gain of oxygen, reduction is the loss of oxygen. So where oxidation is the gain of oxygen, reduction is the loss of oxygen. In terms of hydrogen, reduction is the gain of hydrogen. So oxidation is the loss of hydrogen, reduction is the gain of hydrogen. And finally, in terms of electrons, reduction is the gain of electrons. So it's really important that you learn those, that you learn them in terms of oxygen, hydrogen and electrons, and whether it's the loss or the gain. But essentially if you learn it for oxidation, then you can see that reduction is the opposite. So if I know that oxidation is the gain of oxygen, the loss of hydrogen and the loss of electrons, I know that reduction, being the opposite of oxidation, is the loss of oxygen, the gain of hydrogen and the gain of electrons. So you have to, for a chemical reaction, be able to identify whether it is oxidation that is happening or reduction that is happening. And what you need to spot is, well, is it gaining or losing oxygen? Is it gaining or losing hydrogen? Or is it gaining or losing electrons, and define it in that way. So let's have a look at a few examples to get you into that idea of identifying whether a reaction is oxidation or reduction. So let's look at some oxidation reactions first of all. So we're looking for something that has gained oxygen, lost hydrogen or lost electrons. Here is the definition for oxidation, and that is really important. That is quite often asked in exams. So we can see from our box above that oxidation is something either gaining oxygen, losing hydrogen or losing electrons. Putting that into a definition, we say that oxidation is the addition of oxygen to or the removal of hydrogen from a substance. So essentially, if a substance either gains oxygen or removes hydrogen, but that's just putting it into a more proper definition. That's the definition they would be looking for in your exam. So the first example of an oxidation reaction we're going to look at is the example of rusting. So in simple terms, rusting can be considered as the reaction of iron with oxygen. It also reacts with water, and we'll look at that later in this topic. And that makes it an oxidation reaction, the fact that it reacts with oxygen. So this is very much a simplified equation because water is involved as well. But if we simplify it down, when something rusts, iron is reacting with oxygen to produce iron oxide. So iron has become iron oxide. So if we look just at what's happened to the iron has gained oxygen, and the gain of oxygen is defined as oxidation. And we're going to be writing a lot of these types of explanations, and it sounds like we're repeating ourselves, but what you have to say is, well, what has happened to the iron or whatever is involved in the reaction, and then is that defined as oxidation or is it defined as reduction? So read that carefully. Iron has gained oxygen. The gain of oxygen is defined as oxidation. So you can see here iron is gaining oxygen. There's no hydrogen involved. There's no electrons involved. Well, that we can see from this word equation. Anyway, there will be electrons involved in this. And we would see that iron actually loses electrons and it gives it to the oxygen. But right now we're just looking at it in terms of oxygen. So you relate it to the example that you have. Iron has gained oxygen. The gain of oxygen is defined as oxidation. The second example we're going to look at is the combustion of fuels. Combustion of fuels are always oxidation reactions. Remember that we're just looking at oxidation reactions here. So for example, if we were to burn charcoal, charcoal is almost pure carbon. And when we burn it, it reacts with the oxygen in the air to form carbon dioxide. Let's write a balanced symbol equation for that. So if charcoal is almost pure carbon, we can give it the symbol C. It's reacting with oxygen, which is O2. Remember that oxygen is diatomic, and that is forming carbon dioxide. You should know that carbon dioxide is CO2, but remember, if you didn't remember that, dioxide means two oxygens. So it's carbon, C, dioxide means O2. Okay, so there's your balanced symbol equation. You can see that it's balanced. There's one carbon on the left and on the right, and two oxygens on the left and two on the right as well. So we don't need to do anything to balance that. So we can see here from our balanced symbol equation that carbon has gained oxygen. So it was C and now it's CO2. It literally has taken on, it's bonded with oxygen. So the carbon has gained oxygen. Then what is our second point going to be? Well, what is the gain of oxygen? Is that reduction or is that oxidation? Well, we know that the gain of oxygen is defined as oxidation. So that's what we write as our second sentence. The gain of oxygen is defined as oxidation. So look at how we've structured this answer and learn this format of answer, because it's how we're going to answer all of these questions. So you can see that we've been specific. It's the carbon that has gained oxygen. We don't just say it has gained oxygen. You need to be specific about what has gained oxygen or lost hydrogen or whatever it may be. So carbon has gained oxygen. And then we define that. The gain of oxygen is defined as oxidation. So get into the habit of phrasing it in those ways. A lot of fuels contain hydrogen as well as carbon. And when hydrogen burns, it reacts with oxygen to produce water. We saw that in the POP test. Hydrogen reacts with oxygen to produce water. There's a balanced symbol equation for it. So we look here at the example of methane, which is the gas that we burn in the Bunsen burners in school. Methane has the formula CH4. So it has one carbon atom and 4 hydrogen atoms. We met that in year 11 when we were doing our dot and cross diagrams for covalent bonding. But don't worry too much if you can't remember that formula yet. We're also going to look at it in a later topic in our year 12 course called organic chemistry. So methane is CH4. It reacts with oxygen when we burn it to form carbon dioxide. We know the formula is CO2, and water, which has the formula H2O. Now we need to balance this one this time. So we can see on the left that we have 4 hydrogens, but on the right we only have 2. So how do I fix that? Well, I put a 2 in front of my H2O. And that gets me 2 multiplied by 2 hydrogens, which is 4. So my hydrogens are now balanced. Carbons are fine, so we need to look at oxygens. How many oxygens do we have on the right-hand side? Well, we have 2 as part of carbon dioxide. We now have 2 from our water because we have 2 water molecules, each with 1 oxygen. So we have 4 on the right hand side, but we only have 2 on the left hand side. How do we get 4 on the left hand side? Well, we put a 2 in front of our O2 and that gets us 4 oxygens, and that's our equation balance. Now, if you want, you can write out your list and balance that properly, but that's just a slightly quicker way of doing it. So we can see here that again, this is an oxidation reaction. If we look at it in terms of carbon, first of all, well, carbon is here on the left hand side and it has then become CO2. So carbon has become CO2, so it has gained oxygen. In terms of hydrogen then, we can see that we've got H4 here, and then it's become H2O. So the hydrogen again has gained oxygen, and we know that the gain of oxygen is defined as oxidation. The next example of oxidation that we're going to look at is the rotting of fruit and vegetables. Now, you don't need to know a chemical equation for this. It's just simply if you were asked to classify examples of reactions in an exam, that you could classify this reaction as an oxidation reaction. So you'll all know that if you leave fruit out, especially if it's cut, that it will start to turn brown and eventually will start to mould. And that is an oxidation reaction. So it's the content of the fruit and the vegetables that's reacting with the oxygen in the air, and that's what causes, for example, an apple skin to turn brown or a banana to ripen and then turn brown as well. So rotting of fruit and vegetables is an oxidation reaction. Next, we're going to look at the reaction of magnesium with oxygen. So if we were to burn magnesium, a reaction which you've done many times since first year, magnesium we know is a shiny grey ribbon or a shiny grey solid. It burns with a bright white light to form a white ash of magnesium oxide. What is the equation when we're looking at the reaction of magnesium with oxygen? If you can, have a go at pausing the video, write a word equation and then write a balance symbol equation. If you want, you can check the word equation before you then move on to the balance symbol equation. So try writing a word equation for this reaction and then a balance symbol equation. Okay, let's see how you got on with that. So the word equation should be magnesium plus oxygen and then an arrow, magnesium oxide. Remember, an equation just explains the story of what is happening in a reaction. So magnesium is reacting with oxygen. So those are our starting reactants, so we put them on the left. Magnesium plus oxygen, that literally means magnesium is reacting with oxygen. The arrow means that this is what I'm going to produce when they react together. And what's our product of this reaction? It's magnesium oxide. So writing that word equation should be straightforward enough. If you haven't had a go at the balance symbol equation, pause the video now and try to do that. Okay, so your balance symbol equation with magnesium, it's just Mg. It's not diatomic. I don't include the valency. It's just simply magnesium, the symbol for that element, which is Mg. Oxygen then is O2 because it is diatomic. Magnesium oxide then I need to do swap and drop. So magnesium is Mg. Oxide is just oxygen having become an oxide ion. Need to think of our valencies. So magnesium is in group 2, so it has a valency of 2. And oxygen is in group 6, so it also has a valency of 2. We need to ask ourselves, can we cancel those down? And of course we can. We can divide them both by 2. That cancels down to 1 to 1. So we swap and drop and we get MgO. So those valencies cancel out, and so our formula of magnesium oxide is simply MgO. We need to balance this. Again, you could make your list if you wish, but what you can see quite easily is that there's 2 oxygens on the left, and so we need to put a 2 in front of our magnesium oxide to get 2 oxygens on the right. Remember, we can only put numbers in front of the formulas. And now we have 2 magnesiums on the right, so I need to put a 2 in front of my Mg. So your balance symbol equation should be 2Mg plus O2 arrow 2MgO. So let's have a think about what is happening in this reaction and how we can define it as oxidation. Well, if we look at magnesium here, it has formed MgO. So Mg has become MgO. It has literally gained oxygen. It is bonded to oxygen now. So how would we write our explanation for this reaction? What has happened? Why can we define it as oxidation? Well, we can see it's the magnesium that has gained oxygen. So that's your first point. Magnesium has gained oxygen. And then we need to go on, well, what is the gain of oxygen defined as? The gain of oxygen is defined as oxidation. So you're always saying what has lost or gained oxygen, hydrogen or electrons, and then saying is that oxidation or reduction. Over on the next slide, I'm going to show you this reaction just to remind you of what happens during this reaction. But the key thing here is that magnesium has gained oxygen in this reaction, so the gain of oxygen is defined as oxidation. The final example of oxidation that we're going to look at is the burning of sulfur in air, and you can see all of these burning reactions are oxidation because when you burn something, it reacts with the oxygen in the air and essentially it gains oxygen. It forms an oxide product. Again, I'm going to show you a video of this reaction in just a second, but sulfur is a yellow powder which when you heat it, when you burn it, it melts to form a red liquid which burns with a pale clean blue flame. Heat is released and we form this pungent, choking, colourless gas, and that gas is sulfur dioxide. So again, I'd like you to pause the video, try and write a word equation for this reaction and then a balance symbol equation for this reaction. So think about what's happening, what are you producing, what's reacting together, and write yourself a word equation and then a balance symbol equation. So pause the video and try that now. So let's have a look first of all at the word equation. So we've got sulfur reacting with oxygen. So we simply write sulfur plus oxygen. Literally, sulfur is reacting with oxygen. Then what do we form? We form sulfur dioxide. So over on my right hand side, I just write sulfur dioxide. Balance symbol equation for this then. Well, sulfur is just S. It's not diatomic, so I just write it as S. Oxygen is O2 because it is diatomic. Sulfur dioxide, we write the formula of this in the same way as we write carbon dioxide. Sulfur is S and dioxide means two oxygens, so it's SO2. And you can see that equation is balanced. One sulfur on either side and two oxygens on either side. What I would like you to do now is pause the video and try and write two sentences, just in the same structure as we've done before, to explain why is this an oxidation reaction. So what has happened and why is it an oxidation reaction. So pause the video, you can look back at our previous sentences if you wish, but it's got exactly the same structure. What has happened and why can we define this as an oxidation reaction? So your first sentence should be, sulfur has gained oxygen. So I've written sulfur in green because you always have to be specific about what is losing or gaining oxygen, hydrogen or electrons. So sulfur, you've got to specify what in particular is being oxidized. It has gained, so it's in pink because that word is always going to be either gained or lost. But in this case it has gained, and then in oxygen is in blue because that word's either going to be oxygen, hydrogen or electrons. So sulfur has gained oxygen. So in this particular example, it has gained oxygen. It's gone from S to SO2. What is your second sentence going to be then? The gain of oxygen is defined as oxidation. So you're essentially just saying, well, why is this oxidation? That's because the gain of oxygen is defined as oxidation. So again, I'm going to show you a video of this reaction and then we're going to move on to reduction reactions. The next reaction we're going to do is the reaction of sulfur with oxygen, again by burning it. So when you burn something, it's reacting with oxygen in the air. Hopefully you can see that sulfur is a bright yellow powder, but when we burn it, we're going to see that it's going to change colour, and we'll have a look at the flame that it produces as well. So again, we'll put this on the roaring flame. Okay. So hopefully you can see this. That the sulfur is melting and it forms a red liquid. Hopefully you can see that it's no longer yellow, it's now red and it's forming a liquid. So the sulfur is melting and forming a red liquid. What I want to do is take it out of the flame, and what you can see that even without the flame, it even without the heat, it is burning with a clean blue flame. What we mean by a clean blue flame is one that is not sooty, so clean means not sooty, and you can see the colour of the flame is blue. So it's forming, burning with a clean blue flame, and the gas given off is a very pungent gas, so I'll burn it just a little bit more. Obviously you'll not be able to smell that, but the gas given off is a pungent gas. That means essentially it would like choke the back of your throat, be very smelly gas. And that gas is sulfur dioxide. So when we burn sulfur, it forms sulfur dioxide, and that is a choking, pungent gas. So we're now going to take a look at some reduction reactions. So we're at the bottom of page 4 here. And remember that reduction is the opposite of oxidation. And let's remind ourselves what reduction is in terms of oxygen, hydrogen and electrons. So first of all, it's the loss of oxygen. So if you think about it, oxidation was the gain of oxygen. So since reduction is the opposite of oxidation, it's the loss of oxygen. What do you think it's going to be in terms of hydrogen? It's the gain of hydrogen. Since oxidation is the loss of hydrogen, reduction is the opposite, it's the gain of hydrogen. And then lastly, in terms of electrons, what do you think reduction is going to be? It's the gain of electrons. So where oxidation is the loss of electrons, reduction will be the gain of electrons. So if an atom or an ion gains electrons, we call that reduction. So again, look at your definition. This is a key definition, and you'll notice that it's just the opposite of oxidation. So where oxidation was the addition of oxygen to or the removal of hydrogen from a substance, reduction is the opposite. It's the removal of oxygen from or the addition of hydrogen to a substance. So literally, again, it is the opposite definition of oxidation. So let's look at a few reactions which we can define as reduction. So the first example is chlorine reacting with hydrogen. So you're told here that chlorine reacts with hydrogen to form hydrogen chloride. So chlorine is reacting with hydrogen to form hydrogen chloride. See if you can write a word equation for that, and see if then you can write a balanced symbol equation for that. So pause the video and try and write the word equation, think about what's reacting together to form what, and then try and write a balanced symbol equation. So we can see from the sentence that chlorine is reacting with hydrogen to form hydrogen chloride. So hydrogen chloride is our product. And that's something you need to be confident in doing, taking a sentence, taking a description of a reaction and putting it into an equation form. Let's try writing the balanced symbol equation. If you haven't already tried it, try it yourself first of all, and then go through the video to check. So chlorine is diatomic, so I need to write it as Cl2. Plus hydrogen, it's also diatomic, so I need to write it as H2. Then we've got hydrogen chloride. I'm going to need to use swap and drop to get the formula of this compound. So hydrogen is H, it's up there on its own in the periodic table, and it has a valency of 1. Chloride is just a chlorine atom that has become a chloride ion. So it's just Cl. Remember, when it's part of a compound, it is no longer diatomic. So you don't write it as Cl2. You just write its symbol, which is Cl. Chlorine is in group 7. And so that means its valency is 1. Again, don't think that because it's diatomic that its valency is 2. We go to the group number to get the valency. So up to the top of group 7, they have a valency of 1. And that's because they need to gain 1 electron to get a full outer shell. So swap and drop that, and you get simply HCl. So there's your symbol equation. We need to balance it now. You can see that there's 2 chlorines and 2 hydrogens on the left, but only 1 of each on the right. So how do we fix that? We put a 2 in front of our HCl, and now that equation is balanced. Again, you could write your list if you wished. Okay, so now we need to think about what has happened and how we can define this as a reduction reaction. Well, we can't say anymore that chlorine has lost oxygen, for example. There's no oxygen involved here. So I go to my 3 definitions of reduction up here. Has oxygen been lost? Has hydrogen been gained? Or have electrons been gained? We can't see clearly in terms of electrons here, but we can see that chlorine has gained hydrogen, and the gain of hydrogen is defined as reduction. So chlorine has gained hydrogen. You can see that it's gone from Cl to HCl. So literally by the formula you can see it has gained hydrogen. And what is the gain of hydrogen? It is reduction. So our second sentence is the gain of hydrogen is defined as reduction. So again, if you're explaining why is this reduction, you have to say, well, what is happening first of all? What is gaining hydrogen or losing oxygen, for example? And say that that is then defined as reduction. So just exactly the same format as the sentences we wrote for oxidation. The next reaction we're going to look at is the reduction of copper oxide. And in your Google Classroom, below the video on YouTube, I have put a link to a separate video which shows this reaction happening, and it's worthwhile maybe pausing the video now and having a look at that reaction. You get to see the colour change, and it explains a little bit about the reduction reaction taking place. So we've got copper oxide, and essentially what we're trying to do is we're trying to remove the oxygen from it so that it just becomes water. So we're essentially removing this oxide part to just leave us with copper. And we do that using hydrogen. So we pass hydrogen over the copper oxide once it's been heated. And essentially the hydrogen steals the oxygen from the copper oxide. The hydrogen steals the oxygen and becomes water. And then when the oxygen has been removed from the copper oxides, it becomes just copper. So have a watch at that video to so that you can see the reaction happening and what observations can be made during the reaction. But just to highlight, because this can be asked in the exam, the colour change happening here is, well, we start with copper oxide, which you'll remember from your year 11 studies is black. So copper oxide is black, and then when the oxygen is removed from it, we form just copper, and copper is like a pinky brown colour. It can be referred to as pink, or sometimes it is referred to as pink brown. So it might actually be worth writing that off to the side and highlighting that if you were asked in an exam what colour change takes place during this reaction, you would be writing black to pink brown. That would be 2 marks, one for black and one for pink brown. So you're just thinking, well, what colour is copper oxide and what colour is copper? And that's what it's changing in between. You get a mark for saying pink brown or pink, or sometimes even red brown. So let's have a look at the balanced symbol equation, and I think that really clearly helps us see why this is defined as a reduction reaction. So first of all, we've got the copper oxide, and you can see that there is a 2 in brackets here, which means the valency of copper is 2 in this compound. So we've got Cu with a valency of 2. Oxide is just oxygen that has become an oxide ion, so it's not diatomic anymore, but it is in group 6, which means it has a valency of 2. Those 2 valencies will cancel each other out, and you'll just be left with CuO. Plus hydrogen. Hydrogen's an element, but it's diatomic, so I need to write it as H2. Copper then, that is just the element copper, and it's not bonded with anything, so we don't need to use its valency or anything. It's not diatomic, so we just write it as Cu. Plus water then is H2O, so plus H2O. So what you can see happening here is that copper oxide has been reduced. Why has it been reduced? Well, because it has lost oxygen. So if we look here, and you can circle this in a different colour if you have it, just make sure you know these arrows are not part of the equation. We're going from CuO to just Cu. So copper oxide has lost oxygen. And we know that the loss of oxygen is defined as reduction. Remember, the gain of oxygen is oxidation, so the loss of oxygen must be reduction. So let's write that as our second sentence. The loss of oxygen is defined as reduction. But something has also happened to the hydrogen. So as copper oxide loses the oxygen, what does the hydrogen do? The hydrogen actually picks up the oxygen that is lost by the copper oxide. It steals the oxygen from the copper oxide, and that's because it's actually more reactive than copper. So this is a displacement reaction as such. So hydrogen has gained oxygen And what is the gain of oxygen? The gain of oxygen is oxidation. So hydrogen, we say, is oxidized to water because it has gained oxygen. And what is the gain of oxygen? The gain of oxygen is defined as oxidation. So what we can see here is essentially the oxygen has just moved from the copper oxide to the hydrogen, and that has then become water. So what you can see is happening in this reaction is reduction. So copper oxide is reduced, but actually hydrogen is also oxidized. We've got reduction and oxidation taking place in the same reaction. And that is what we call a redox reaction. So this definition is really important. When oxidation and reduction occur simultaneously, that just means at the same time, in the same reaction, it is referred to as a redox reaction. Where do we get this name redox from? Well, the RED at the start of the name, red, stands for reduction, and the ox at the end of the name stands for oxidation. So this is really important. This reaction that we've just looked at is what we call a redox reaction, because oxidation and reduction are occurring simultaneously at the same time in the same reaction. So quite often it's a 2-mark question in an exam. What is meant by a redox reaction? So let's just write an explicit definition down here so that you have that and can learn that. So your definition would be a reaction in which reduction and oxidation occur simultaneously in the same reaction. And the word simultaneously is important because it must happen at the same time. The two things must happen hand in hand. Essentially, one thing's reduced as the other thing is oxidized. And it must be in the same reaction. You can't have one reaction taking place that is reduction and a separate reaction taking place that is oxidation and just call it redox. No, it must be happening in the same reaction. So what we've just looked at, copper oxide and hydrogen reacting together. The copper oxide is reduced because it loses oxygen at the same time as the hydrogen is oxidized because it picks up oxygen. It gains oxygen. So redox reaction, really important definition, is a reaction in which reduction and oxidation occur simultaneously in the same reaction. So what have we learned so far? We've looked at oxidation and reduction reactions. We've looked at how oxidation is the gain of oxygen and reduction is the opposite. It's the loss of oxygen. We've also seen how oxidation is the loss of hydrogen, so it's opposite in terms of hydrogen. Oxidation is the gain of oxygen, but the loss of hydrogen. And then reduction is the gain of hydrogen. So we've looked at examples now of reactions of oxidation and reduction in terms of oxygen and hydrogen. And we've also looked at redox and how that is reduction and oxidation occurring simultaneously in the same reaction. In the next section, we're going to look at what oxidation and reduction are in terms of electrons. So for the rest of this video, we're going to look at oxidation, reduction and redox reactions in terms of electrons. So we've already touched on this at the start of the video, that oxidation is the loss of electrons and reduction being the opposite of oxidation, it's the gain of electrons. And to help you remember that, you can think of the little rhyme oil rig. Oxidation is loss, reduction is gain. So in terms of oxygen and hydrogen, you need to learn which way around it is. But this works for electrons, that oxidation is the loss of electrons, reduction is the gain of electrons. Think of oil rig. So essentially, if an atom or ion loses electrons, we call that oxidation. If an atom or an ion gains electrons, we call that reduction. So let's take, for example, that reaction we've already looked at of magnesium reacting with oxygen. We know that it burns with a bright white light. It forms a white ash of magnesium oxide. And we've described this as an oxidation reaction because magnesium has gained oxygen. So when magnesium reacts with oxygen, it's an oxidation reaction because magnesium is gaining oxygen. So again, pause the video, try and write a word equation for this, and then a balance symbol equation for this reaction. So pause the video now and try and write a word equation and a balance symbol equation. So magnesium and oxygen are reacting together, so they are our reactants, they go on the left. then our arrow shows us what we're forming, and we're forming magnesium oxide. Let's convert that into a balance symbol equation. We've got magnesium, which is Mg. Remember, we don't include valencies or charges when it's just an atom. Oxygen is O2 because it's diatomic. Magnesium oxide, we need to do swap and drop. So magnesium's in group 2, has a valency of 2. Oxygen is in group 6, so it has a valency of 2. Those cancel out, and so we just have MgO. This needs to be balanced. We've got 2 oxygens on the left, but only 1 on the right, so I need to put a 2 in front of my magnesium oxide. That gives me 2 magnesiums, so I need to put a 2 in front of my magnesium on the left. So we can see that magnesium has been oxidized because it has gained oxygen. It has gone from Mg to MgO. So we can say that magnesium has been oxidized because it has gained oxygen, and the gain of oxygen is defined as oxidation. But we can also think of this in terms of electrons. So if we were to write a half equation for this reaction, it would be Mg going to Mg2 plus 2 electrons. We'll have a look in a second about how we get that, how we write half equations from a balance symbol equation. But if we just look at the equation that has already been written for you in this box, we can see that Mg has become Mg2+. So what has happened to it? It's gone from Mg to Mg2+. What has happened to form Mg2+? Well, it must have lost 2 electrons, and we can see that because the electrons are on the right hand side of the equation. But we know that to form a positive ion, we need to lose electrons because electrons are negatively charged. How many electrons has it lost in order to form a charge of 2+? Well, it must have lost 2 electrons. So we're being as specific as we can here and saying that the magnesium atom has lost 2 electrons to form a magnesium ion with a charge of 2+. The loss of electrons, is that oxidation or reduction? Remember, oil rig, oxidation is loss. So the loss of electrons is defined as oxidation. Therefore, this is an oxidation reaction. So you're having a look at your atom or your ion and you're thinking, has it lost electrons? Has it gained electrons? And then thinking, is that oxidation or reduction? So in this reaction, the reaction of magnesium with oxygen, we can see that it's oxidation because the magnesium has gained oxygen, which is oxidation. But we can also see that magnesium has lost electrons, which is also oxidation. So let's have a quick look at how you write half equations from a full equation, and that will become really important later on in this topic. So let's take the balance symbol equation of the reaction we have just looked at. So that is magnesium reacting with oxygen. So you may be wondering, well, how do I tell whether the atom has a charge or not, whether it's an ion or whether it's just an atom? Well, the easiest way to think about it is that if it's on its own, then the element has no charge. So if the, and this will be particularly referring to metals, if the element is on its own, so it's an element, then it has no charge. Okay, so if it's on its own, it has no charge. If it is part of a compound, in other words, if it's magnesium oxide or sulfur dioxide or whatever it may be, if it is part of a compound, then it will have a charge. So you can see in the right hand side, it's magnesium is part of magnesium oxide, then it will have a charge. So if it's part of a compound, it will have a charge, and the charge will be related to its group number. So this is where you need your periodic table, and if you haven't got that out already, you should have that out. And we always relate the charge and the ion to the group number. So for example, group 1 form ions with a charge of +1. Group 2 form ions with a charge of +2. So if we're trying to write a half equation from this balance symbol equation, let's look at the left hand side first of all. So we're just looking at what is happening to magnesium. So on the left hand side, magnesium is on its own on the left hand side. So on the left hand side in our half equation, it's going to be written as just simply Mg, because if it's on its own, remember the element has no charge. On the right hand side, however, magnesium is part of a compound, and so it must be written as an ion with the charge associated with this group. Look at your periodic table, you can see that magnesium is in group 2, which all form ions with a charge of +2. But remember, when we're writing the formula, the number of the charge comes first. So it's written as Mg2+. So rather than writing +2, you write Mg2+. So we can start to write that into a half equation. So what's happening on the left hand side is magnesium, Mg. I'm forgetting about my oxygen for now, just focusing on magnesium. Mg is forming an ion of magnesium, Mg2+. So there's where our half equation starts. But that's not the full story, because we must balance our half equation. So we can see that it's balanced in terms of the atoms, but it's not balanced in terms of the charge, because magnesium has no charge on the left hand side, but has a charge of 2+ on the right hand side. And this is where we come back to our year 11 studies, and we remember that we balance a half equation in terms of the charge by adding electrons to the left hand side or right hand side. Let's just do a quick recap of how we represent electrons in a half equation. We write it as E minus, with that little minus as a superscript on the top right hand corner. And what is the charge on an electron? The charge is -1. So when you add an electron to either side of the equation, that's going to bring the charge of that side of the equation down by 1. So let's write the half equation as we have it so far. And if you remember from writing our half equations, what we did was work out what's the charge on the left and what's the charge on the right hand side. Well, the charge on the left, there is no number in the top left hand corner. There's no number here, so that means there is a charge of 0. So there's no plus, there's no minus, and so the left hand side has a charge of 0. What about the right hand side? It has a charge of +2. So you're asking yourself which side needs to drop in charge. So when you're deciding which side of the equation to write your electrons on, you're thinking which side needs to drop in charge, because we need these charges to match. So if, say for example, I was to put the electrons on the left hand side, the charge would go down and down and down as I add electrons, and that would just come further and further away from +2. So you can see that actually I need to add electrons to the right hand side to bring them down. So I'm writing what I already had, Mg, arrow Mg2+, and then I'm writing plus electron on the right hand side. But I need to think, well, how many electrons do I need to get these charges to match? So if I add an electron to the right hand side, you can see that that would bring my overall charge down to +1, because I've got a 2+ here and then minus, so 2 minus 1 essentially is still +1. So I actually need 2 electrons in order to cancel out that +2 charge, because originally our charge on the left was 0 and our charge on the right was +2. But now that we've added these 2 electrons, that has brought the charge on the right hand side down to 0, which matches the left hand side. And we can see from this half equation that magnesium is losing electrons. So think of this magnesium atom on the left. It is essentially losing 2 electrons, forming an ion of 2+, and then those electrons are essentially spare. So the magnesium atom is losing electrons. And what do we call the loss of electrons? We call it an oxidation reaction. Remember, oil rig, oxidation is loss. So you need to be confident in writing half equations from a balanced symbol equation, and we'll do a little bit more practice of that as we go through the topic. And then just quickly to note before we move on to another example is just how we identify whether an atom or ion is losing or gaining electrons, and it all depends which side of the equation that the electrons appear on. And you may be able to see this, you may be able to understand this by looking at an equation, but if you're struggling with it, it's worth actually learning that if they appear on the left, it's this type of reaction. If they appear on the right hand side, then it's this type of reaction. So let's look first of all, if the electrons appear on the left hand side as they are in this reaction, and this is just an example where X is a random element, so X2 plus. So you can see we've got an ion with a charge of 2 plus. We are adding on 2 electrons and we're forming an atom with no overall charge. This means the atom or ion is gaining electrons if they are on the left hand side. You can see we're literally adding them on. So the ion or the atom involved is gaining electrons. What is the gain of electrons? It is reduction. The gain of electrons is reduction. So I think you can see it a little bit easier if it's on the right hand side, that the atom or the ion is gaining electrons. If the electrons, however, appear on the right hand side, it's a little bit harder maybe to see this, but if the electrons appear on the right hand side, that means the atom or ion is losing electrons. Essentially, X is shedding off electrons and they are then being produced as a product. And if it is losing electrons, what is the loss of electrons? The loss of electrons is oxidation. So if you struggle to understand that by just looking at an equation, it might be worth learning. Electrons on the left is gaining electrons, and so is reduction. Electrons on the right means that the atom or ion is losing electrons, and that's oxidation. Let's have another look at this idea of oxidation or reduction reactions in terms of electrons. And this time we're going to look at a reduction reaction. And this is a reaction that we're going to study in greater detail at the end of this topic when we look at something called the blast furnace. The blast furnace is how we industrially extract iron from its ore. And iron is obviously a very useful metal, so it's a really important process. But this equation represents the process that happens in that blast furnace. So in extracting iron from its ore, iron oxide is reduced to remove oxygen from the compound in order to obtain pure iron. So if we want iron from iron oxide, we've got to remove the oxygen. So you can see your equation has been written for you here, and we are going from iron oxide, Fe2O3, to iron. So iron oxide is losing oxygen to become pure iron. What is the loss of oxygen? It is reduction. So in terms of our iron oxide, this can be described as a reduction reaction, as the iron oxide has lost oxygen. So we can see clearly here, and from our equation, that in terms of oxygen, this is a reduction reaction. However, if we consider only the iron ion within the ore, so forgetting about the oxide part of it, we can see that there's a change in number of the electrons as well. So what we need to do is write a half equation in terms of iron. And what we need to go back to is remembering, well, is it an atom? Is it an ion? How can we tell that? So let's highlight the things in our equation that are that have iron in them. So on the left hand side we have iron oxide. That is a compound. So remember, this is going to be an ion. It is going to have a charge. So this, our iron within iron oxide is going to be an ion. We said then if the element is on its own, then it will not have a charge. So we can see on the right hand side, iron is on its own, and so that's not going to have a charge. So you can highlight that and add that into your notes if you think that would be helpful. So on the left hand side, we're going from an ion to, on the right hand side, an atom with no charge. This is a little bit more tricky because iron is in the transition block of elements, so it won't have a charge related to its group number because it doesn't have a group number. It's in that transition block because those metal ions can form ions with different charges. So there's a couple of ways that we can think about getting the charge on this ion. The first thing we can do is simply look at the name and look at the number that's provided for us. So we can see here that it's iron 3 oxide. That means the iron has a valency of 3, and we can think of that as meaning it has a charge of 3 plus. So that 3 in brackets means that the charge is 3, and it's positive because metal ions are always positive. So we can see within this compound of iron 3 oxide, the iron is going to have a charge of 3 plus. There's another way we can think of it too, and that's essentially by doing a reverse swap and drop. So you can see here that my formula is Fe2O3. How did we get that formula? Well, before we dropped our valencies down so that they were subscripts, they were written down at the bottom instead of at the top, we would have swapped them. So that 2 would have come from the oxygen, and the 3 would have come from the iron. So what we would have started off with was Fe3O with a valency of 2. Can you see how I've done reverse swap and drop here? I have swapped and raised essentially. And we can see from that iron would have originally had a valency of 3, which means that it has a charge, again because it's a metal ion, it's positive, it's Fe3 plus. So there's two ways of working out what the charge on this ion is if it's a transition metal element. If it's a metal in group 1 or group 2, it's easy. We can see the charge from the group number. This is a little bit more tricky. So firstly, you can see it from the number in the brackets, but you may not be given a number in brackets. You may have to work it out from the formula, in which case you think about reversing the swap and drop. Think, well, what would have the charge been on the original ion before you swapped and dropped it with your oxygen? So either way, we can see that the iron ion on the left-hand side has a charge of 3 plus, and we know that it's an ion because it's part of a compound. Remember, if it's part of a compound, it will have a charge. So on the left hand side, if we're writing the half equation now, we would write Fe3 plus. That is then reacting to give, on the right hand side, remember we're back here now, and we're producing iron. Remember, it has no charge because it's on its own. So if something is on its own, it will have no charge. Now we need to balance our half equation in terms of charge, and we do that by adding electrons to one side of the equation. So let's think of the charge on either side of the equation at the minute. On the left hand side we have a charge of +3 overall. On the right hand side we have no charge. There's no positives, no negatives, so the charge is 0. So we need to add electrons. Which side do I add it to? Remember, we add to the side that needs to go down in charge. Remember, electrons are E minus. They have a charge of -1. So which side needs to drop in charge? It needs to be the left-hand side. So we add our electrons to the left-hand side. How many do we need to cancel out that charge of +3? Well, each electron has a charge of -1, so I need 3 of them. So you can see from my iron, it has 3 positive charges. My electrons, there's 3 negative charges. That brings it down to 0. So +3 cancels out with -3. And you can see the charge on either side of the equation is now 0. So what has happened in terms of electrons? What can we see from our equation? Well, we can see that the electrons are on the left-hand side of the equation, and that means that electrons have been gained. So the iron ion, it's important that you say the iron ion because it is an ion on the left-hand side. We start with the ion. It has gained electrons and it has become an iron atom. And remember, we want to be as specific as we can, so we need to say it has gained 3 electrons. So specify the number of electrons that it has gained. So the iron ion has gained 3 electrons to become an iron atom. We say then that the gain of electrons is defined as, well, is this oxidation or is it reduction? So remember, oil rig, oxidation is loss, reduction is gain. So the gain of electrons is defined as reduction. Therefore, this is a reduction reaction. So we can now see that in terms of oxygen, it is a reduction reaction, because iron oxide has lost oxygen to become iron. And we can also see now from our half equation that the iron ion is gaining electrons, and again that is defined as a reduction reaction. And the last example we're going to look at is the extraction of aluminium. So we just looked at the extraction of iron, and we're now going to look at the extraction of aluminium. Again, aluminium is extracted from its ore, which is called bauxite, and we use a process called electrolysis, which we'll look at in the next topic. And in this case, aluminium is separated from its ore, which is mainly consisting of aluminium oxide, and it's split up using electricity. So we're told here that the aluminium ions are attracted to the cathode, which is the negative electrode, and it picks up electrons to become an aluminium atom. So we can write a half equation from that, or we can write it from the balance symbol equation. So let's try and write it just from the information that we have been given first of all. So we can see that the aluminium ions, that's what we start with, and we're told here that they have the formula 3+, Al3+. That is forming the aluminium atom. So that's forming an aluminium atom after it picks up electrons, and that has the formula Al. So let's have a think in terms of electrons. What has happened? We're told that it picks up electrons, but how many? So it picks them up, that's suggesting they're going to be in the left hand side, it gains them. But even if we look at the charge, we can see that on the left hand side the charge is +3, on the right hand side the charge is 0. And so it's the left hand side that needs to go down in charge. So that's where I add my electrons. How many do I need? I need 3 electrons. Let's have a think from our word equation and our balance symbol equation as well. We can see from our word equation that this is a reduction reaction because aluminium oxide is losing oxygen. To write our balance symbol equation, we need to use swap and drop. So for aluminium oxide, we've got Al, aluminium. It's in group 3, so it's going to have a valency of 3. Oxide is oxygen that has become an oxide ion. It is in group 6, so it has a valency of 2. So if we swap and drop those, they can't cancel down. So it's Al2O3. That reacts to give us aluminium, which is just Al. It's not diatomic. We don't include the charge because it's now an atom. And we form oxygen as well, which is O2. The balancing of this equation is a little bit complicated. You'll actually need to put a 3 in front of your O2, that gets us 6 oxygens, a 2 in front of the aluminium oxide, which gives us 6 oxygens, and then you can see that we've got 4 aluminiums on the left, and so we need to put a 4 in front of our Al on the right. Don't panic about that, I know I went through that very quickly. You can go through it step by step and do it if you wish, but that's not our main focus. What we want to look at is how we could get our half equation from this balance symbol equation. So again, with the aluminium, that's what we're focusing on. We're focusing on the aluminium from this. There's a couple of ways we can get the charge of our aluminium. So first of all, we need to decide which side of the equation is our aluminium in the ion form. Well, remember, when it's part of a compound, which it is in the left hand side, is aluminium oxide, we are going to have an ion with a charge. When it's on its own, as it is on the right hand side, it's going to be an atom with no charge. So we are going from an ion to an atom. A couple of ways we can work out the charge on our ion on the left hand side is going to be Al. The first way we can work out the charge is by looking at its group number. It's in group 3, which means it's going to form a charge of +3, and we write it as the formula as Al3+. Or we can do what we did up here, essentially our reverse swap and drop. So you can see that the formula of your aluminium oxide is Al2O3. If we were to do reverse swap and drop, you can see that the 3 originally belonged to the aluminium, which means it had a charge of 3+ because it's a metal ion, and remember they're always positive. And then we are going on the left hand side to an aluminium atom, so I simply write it as Al with no charge. And then what side do I need to add my electrons on? To the left hand side to get that to come down in charge. And how many do I need? I need 3 to balance out that charge. So that's just showing you how you could have got that from the word equation and the balance symbol equation. So let's have a look again at our half equation, and let's see what's happening in terms of our electrons and how we can then define that as what type of reaction it is. So we're looking at this equation here again. So you can see that reading from left to right, the aluminium ion has gained 3 electrons. Those electrons are on the left hand side, which means it's gaining electrons. So electrons on the left hand side of the equation means gain of electrons. So the aluminium ion has gained, and again we want to be specific, we can see that it has gained 3 electrons and it has become an aluminium ion. Therefore, since it has gained electrons, again think oil rig, oxidation is loss, reduction is gain, and we're gaining electrons here, so it must be a reduction reaction. And the next bit just says that reduction always happens at the cathode in electrolysis, oxidation happens at the anode. Don't worry about that for now, we'll come back to that in our electrochemistry topic. What I'd like you to do now is take a break from listening to me for just a couple of minutes and to try some questions on what we've covered so far. So to quickly recap what we've covered so far, essentially we can summarise it by, we've learnt that oxidation is the gain of oxygen, the loss of hydrogen or the loss of electrons, and reduction is the opposite. It's the loss of oxygen, gain of hydrogen, and the gain of electrons. Not all of these have to happen in the one reaction for it to be defined as oxidation or reduction. So for example, if you see a reaction where there's a loss of hydrogen, that is oxidation. So what I'd like to do is turn to page 14, and in your workbook or on a separate file page if you want to keep this separate and maybe in a folder for your year 12 work, that might be a good idea. I want you just to complete question 1 for now, and then we'll do a little bit more, and then you can complete the rest of these questions, and that'll finish the first section of this topic. So you can see here you've been given 7 different reactions, and you've just been given the equation for them. Sometimes a balance symbol equation, sometimes a half equation. And what you need to do is decide whether they are oxidation or reduction, and then explain fully why it is classified in this way. So make sure you don't just write oxidation or reduction. You've got to explain why. And what I want you to use is use that 2-sentence structure that we have been doing since the start of the topic. So such and such has lost hydrogen. The loss of hydrogen is defined as oxidation, for example. So let's look at this first example to show you what I mean by this. So in your book, I would like you to write out the equation first of all and then explain. So write out the equation and then explain. And you can see in this reaction that calcium has gained oxygen. The gain of oxygen is defined as oxidation. So having a look at that equation, you can see that calcium is going from Ca to CaO, and so that shows us that calcium has gained oxygen, and we know that the gain of oxygen is defined as oxidation. So that's all that you need to write, 2 sentences for each of them. So you're looking essentially to see, has something gained or lost oxygen, hydrogen or electrons, and then think, is that oxidation or is that reduction? But keep your explanations in that same format. Calcium has gained oxygen. The gain of oxygen is defined as oxidation. And just a quick note down, for example, for part D, you can see here that we've got a lithium ion. So when you're doing your explanation, you need to say the lithium ion has, and then whatever it is. Okay, so try and decide whether these are oxidation or reduction, and explain them in terms of whether they have gained or lost oxygen, hydrogen or electrons. So pause the video now, try these, and then I'll go through them really quickly before we move on, just to check that you've got the right idea of what oxidation and reduction is. So make sure you've tried these yourself before going through these, but I'd like to check them with you briefly just to make sure that you've got them right. So we've gone through the first one, and we have our summary there of what oxidation and reduction are in terms of oxygen, hydrogen and electrons. So let's look at B first of all. So what is happening here? Well, we can see on the left hand side we have hydrogen iodide. HI is hydrogen iodide. Okay, and that's splitting up, and the hydrogen and the iodine are essentially splitting up. So we can see it's not going to be anything to do with the iodine, but you can see HI is forming I2. And so essentially hydrogen iodide has lost hydrogen to become just iodine. So hydrogen iodide has lost hydrogen. That's going to be your first sentence. So hydrogen iodide has lost hydrogen. What is the loss of hydrogen defined as? So we need to find it in our list essentially. Here we have it. The loss of hydrogen is defined as oxidation. So B is also oxidation. So that would be your second sentence. The loss of hydrogen is defined as oxidation. So that's the format of the explanations that you need for each question. Let's look at part C. Well, we're starting with sodium, Na, and it is forming NaH. So you can see here that sodium has gained hydrogen. It has taken on a hydrogen atom. So that's your first sentence. And then we need to decide, well, what is the gain of hydrogen? Let's find it on our list. Here we see it here. The gain of hydrogen is defined as reduction. So your second sentence will be, the gain of hydrogen is defined as reduction. So that's part C. Let's move on to part D now. What is happening in this reaction? Well, you can see we start with a lithium ion. It's an ion because it is charged, and it is becoming a lithium atom. How is it doing that? Well, it's gaining an electron. So your first sentence is going to be, the lithium ion is gaining one electron. And what is the gain of electrons? Is it oxidation or is it reduction? So again, look at our list and we can see that the gain of electrons is defined as reduction. So that is your second sentence. The gain of electrons is defined as reduction. So again, you're saying what has happened in terms of the gain or loss of oxygen, hydrogen or electrons, and then is that oxidation or reduction. Part E then, what is happening? Well, what are we starting with first of all? We're starting with Br, which is the symbol for bromine, but you can see it has a charge on it. It's negatively charged, so remember, when an ion is negatively charged, it changes its ending to IDE. So we're starting with a bromide ion. So that's what we need to use in our explanation. So our bromide ion, it's forming bromine, and what's it doing in the process? Well, we've got 2 electrons being produced on the right hand side. So remember, electrons on the right hand side means that it's the loss of electrons. So see, it's more difficult to say it this way when they're on the right hand side, but we're losing electrons. So the bromide ions have lost electrons, and so essentially they're produced on the right hand side. So we're saying here that the bromide ion has lost electrons. And if you want to be specific about how many, in this case you can see that 2 bromide ions are forming 2 electrons, so they have lost 1 electron each. So the bromide ions have lost 1 electron each, essentially you would be saying there. It's not to say the bromide ions have lost electrons, and then we need to decide, is that oxidation or reduction? Well, we can see that the loss of electrons is defined as oxidation. So your second sentence for part E is the loss of electrons is defined as oxidation. So give yourself a mark for that if you got that. Part F then, we've got zinc forming an ion of zinc with a charge of 2+. Our electrons are on the left hand side, but we can see from the charge anyway it's become 2+, so that means it's lost 2 electrons, but we can see that because the electrons are on the right hand side, that means it has lost electrons. And we can see specifically that it's lost 2 electrons. Then we need to decide whether that's oxidation or reduction. What is the loss of electrons? It is oxidation. So your answer is zinc has lost 2 electrons. The loss of electrons is defined as oxidation. And then finally in part G, we can see that we start with nitrogen and that we form NH3. NH3 is ammonia, if you remember from year 11. So what has nitrogen gained? We can see that it has gained hydrogen. And then we need to decide whether that's oxidation or reduction. So the gain of hydrogen, that is reduction. So your second sentence would be, the gain of hydrogen is defined as reduction. So hopefully you find those okay, but again, just remember the main summary of what oxidation and reduction are in terms of oxygen, hydrogen and electrons. The last main part of this section is looking at redox reactions in terms of electrons, and then we just have to look at a few industrial examples of oxidation, reduction and redox, and that will be this section of the topic finished. So let's quickly remind ourselves that redox means reduction and oxidation occurring simultaneously in the same reaction. So reduction and oxidation taking place. And these reactions will mainly look at displacement reactions, which will involve two metals. We haven't covered unit 2.1 yet, but you'll remember from your junior science, displacement reactions are more reactive metals taking place of a less reactive metal. Or last year we in our year 11 content we looked at displacement reactions of halogens, where a more reactive halogen will take the place of a less reactive halogen. Generally this will happen in a solution, or it could be a metal oxide. If you put in a more reactive metal, that will take the place of the less reactive metal. Essentially it will steal the oxygen. It's not too important that you understand displacement reactions at this point, but it is important that you can look at an overall reaction and explain why it's redox, why is reduction and oxidation happening in the same reaction. So in order to do that, we need to split up the overall equation into two half equations to represent what is happening to each metal. So you can see in this example we have got magnesium and we have got copper. So we need to write a half equation for each. But let's again think about when will they be an atom and when will they be an ion. Okay, so remember the rule was if the element is on its own, then it's going to be an atom. In other words, it will have no charge. So let's see where the elements are on their own. You can see on the left hand side we have magnesium on its own, and on the right hand side we have copper on its own. So magnesium on the left and copper on the right will be atoms. In other words, they will have no charge in the half equation. Then where will our ions be? Well, you can see here on the left hand side we have copper as part of copper sulfate. That's part of the compound. It's a solution, you can see from the state symbol of aqueous. So copper on the left will be an ion, and magnesium on the right will be an ion because it's part of a compound. So the rule is if it's part of a compound, it will be an ion with a charge. So it's worth identifying that from the main equation at the start to help you when you write your half equation. So then what we need to do is take each one of these metals in turn and write a half equation for them. So let's start with magnesium and have a look at what's happening to it. Well, it's going from Mg on the left hand side to Mg on the right hand side, but it's an ion. So we're going from Mg as an atom, in other words, no charge, on the left hand side. Then let's write our arrow, and we're forming a magnesium ion. Well, what's the charge in the magnesium ion going to be? Well, we need to look to the group number. So magnesium is in group 2, and so it will form an ion with a charge of +2. But we write the formula as Mg2+. So that's all based on its group number. So you need your periodic table out in front of you for doing these. So there is part of your half equation written. Now we just need to balance it in terms of the electrons. So let's have a think. On the left hand side, our charge is 0. On the right hand side, our charge is +2. So we need to think what side needs to come down in charge. Well, that is the right hand side. So we add our electrons to the right hand side, but how many do we need to balance the overall charge? We need 2 electrons to cancel out that 2+ charge of the magnesium. So there's your half equation written. So you're thinking on the left hand side, is it an atom or an ion? On the right hand side, is it an atom or an ion? And that's why it's helpful to have identified that from the main equation at the start. So let's think what's happening to the magnesium in terms of our electrons. And what I would advise at this stage is think about, well, what side are your electrons on and what does that mean? In this case, the electrons are on the right hand side. What does that mean? Are they being gained or are they being lost? They are being lost. So electrons on the right hand side means loss of electrons. Would be magnesium has lost 2 electrons. So you're literally putting your half equation into words. So magnesium has lost 2 electrons. Then we need to write our explanation sentence. Well, what is the loss of electrons? Remember, in terms of electrons, we can think of oil rig. Oxidation is loss, reduction is gain. And so we can see here that this is oxidation. So we can see from our half equation that magnesium has lost 2 electrons. And then we need to write the loss of electrons is defined as oxidation. Then we need to do exactly the same in terms of copper. So copper on the left, we have identified that it is an ion and it is forming an atom on the right hand side. So we've got copper as an ion on the left hand side. So we need to think about the charge on our copper ion because it is in the transition block, so we can't tell the charge from our group number. So there's a couple of different ways you can do this. If you look at the back of your periodic table, you'll see that you're told there that copper has a charge of 2+. So we would write it as Cu2+. The other way to think about it is by the formula of copper sulfate. The formula is CuSO4. And what you should know, or what you can see from the back of the periodic table, is that the sulfate ion, SO4, has a charge of 2-. And so therefore, to cancel that 2- charge out, copper must have had a charge of 2+. Or you can think of it as reverse swap and drop. Sulfate would have had a valency of 2 from its 2- charge. And so therefore, in order for that to cancel out, copper must also have had a valency of 2. Which means that the copper ion has a charge of 2+. So a couple of ways that you can work out the charge on the copper ion. That is forming a copper atom. So we draw our arrow, and our copper atom on the right hand side will have no charge. Remember, atom means no charge. So again, we need to balance this half equation in terms of its charge. So our charge on the left hand side is +2 from our copper ion, and there's no charge on the right hand side. It has a charge of 0. So what side do I need to add my electrons to? I need to add my electrons to the side where it needs to come down in charge. So that in this case is the left hand side. So add my electrons to the left hand side. How many am I going to need to cancel out the 2+ charge of my copper ion? I'm going to need 2. So my half equation in terms of the copper ion is Cu2+ plus 2 electrons gives me Cu. The next thing I need to do is just put this half equation into words, so explain what is happening, but in words this time. So what is happening in terms of electrons? Well, in this case, the copper ion is gaining electrons. And if you can't see that easily from the half equation, remember to learn the rule of electrons on the left hand side means that the gain of electrons is happening. So your first sentence is going to be the copper ion has gained 2 electrons. And what is the gain of electrons? Well, remember from our oil rig that the gain of electrons is defined as reduction. So in the second part of the question, we have written a half equation for copper, and we have explained that half equation in words. So what we've seen so far is that magnesium has lost electrons. So magnesium has been oxidized. Magnesium has undergone oxidation. The copper, on the other hand, has gained electrons, so it has been reduced. It has undergone reduction. Where we have reduction and oxidation occurring simultaneously in the same reaction, that is what we call a redox reaction. So essentially the last thing you need to do to finish off your explanation for this question is to write the definition of a redox reaction. And so you simply have to state that a redox reaction is reduction and oxidation occurring simultaneously in the same reaction. You've proved that reduction is taking place with the copper. You've proved that oxidation is taking place with the magnesium. And because this is happening in the same reaction, it is a redox reaction. So this is probably the hardest question you could get within this topic, and it's really important then that you have practice of taking a balanced simple equation and splitting it into two half equations and explaining why reduction and oxidation are taking place in the same reaction. It would be worth around 5 marks for this type of question, so it's really important that you know how to do this. The format is always going to be the same. You always need to write 2 half equations, explain why one of the half equations is reduction, one of the half equations is oxidation, and then simply state your definition of redox. So if you found that quite tricky, maybe watch that again rather than trying to take down at the same time. Go through that again and make sure you fully understand how we got those half equations and what those half equations mean. The good news about these type of questions though is that the format is always going to be the same for a displacement reaction. Essentially it will just be the metals that will change. And it's just really important that at the start, as we did in the example above, that you identify where the metal is an ion and where the metal is an atom. So in a displacement reaction, the metal originally in the solution or as part of the metal oxide, say for example, so in the solution means that it will be a compound, and so it will be an ion. So that means it's an ion on the left hand side, and the ion will become an atom. And remember, an atom has no charge, and that will be on the right hand side. So the metal originally in the solution will be your less reactive metal, and it will be an ion on the left hand side, and it will become an atom on the right hand side. Because metal ions are always positive, if we want them to go from an ion to an atom, they must gain electrons. The number of electrons will depend on the charge of the metal. It will gain as many electrons as it has charge. So for example, if it has a 3+ charge, it will need to gain 3 electrons. So the less reactive metal is always reduced. So it will always undergo reduction. So in that sense, if you're able to identify the metal that is in the solution on the left hand side, so in the example we've just done, that was copper, it will always go from ion to atom, so in other words charge to no charge on the right hand side. It will be gaining electrons, so the electrons will be on the left, and that will be the metal undergoing reduction. The more reactive metal which is added in this case it was magnesium, is initially an atom, so remember it's on its own, so it will have no charge on the left hand side in this case. It then becomes the ion, so in this case we're becoming an ion on the right hand side. If we're forming a positive ion, and remember metal ions always are positive ions, then we are going to be losing electrons. So the metal that starts as an atom on the left hand side will always lose electrons to become a positive metal ion, and so the more reactive metal, if it's losing electrons, is undergoing oxidation, and we say it has been oxidized. And essentially the electrons that it loses, the more reactive metal loses, are gained by the less reactive metal. That's why this is all happening simultaneously in the same reaction. The ionic or half equations will only involve the metal atoms or ions, not the sulfate or the nitrate or the oxide, but the metals are originally bonded with in the solution or the metal oxide. And just be careful, sometimes the questions are phrased as ionic equations, but really they should be called half equations, but just if the question in the exam says write ionic equations to demonstrate this, you need to remember that essentially that means a half equation, just involving the metals. So it's really important that you essentially learn the format of that answer, which is essentially 2 half equations, 2 explanations of which is being oxidized, which is being reduced, and then your definition of redox. So there's the general format of your answer. Your reduction, half equation can be first. Doesn't matter which way round they come, as long as you've got half equation, explanation, half equation, explanation, and then the definition of a redox reaction. So what I'd like you to do is have a go at this example yourself. You may want to do it on a scrap piece of paper, or you can do it down in the bottom section of this page and then write the answer as I go through it in the bullet points here. But do have a go at this question yourself, because it's really important that you can do this by yourself. And not just write in the answer that I put in. I will give you a head start just because this is a little bit trickier, because we've got two transition metals here and sometimes it can be hard to tell the charge on it. So again, you need to identify where the metal is an ion and where it is an atom. So remember, it's an ion when it's part of a compound. So here are our compounds here, essentially when they're part of this solution. You can see the AQ there, meaning it's part of a solution. So that's where our metals are going to be ions, and when they are on their own, they are atoms with no charge. Then the question is, what is the charge on the ion going to be? Well, there's a couple of ways you can identify this. For iron, first of all, you're told in the question that it's iron 2. That means, remember, metal ions are always positive, so that means the charge on your iron ion is going to be 2+. It's going to be Fe2+. The other way you could work that out is by the formula of iron nitrate. You can see that iron nitrate has the formula FeNO3 2. That means there is one iron ion, and it means there are two nitrate ions. If you look at the back of your periodic table, you'll see that nitrate ions have the formula NO3-, and I have two of them. So each of those nitrate ions has a charge of -1. That gives us an overall charge of -2. So we need to think, well, what charge must the iron ion have to balance out or cancel out that charge? Therefore, it must have a charge of +2. Then let's briefly think about the charge in your zinc ion. Again, two ways you can do that. The charge of a zinc ion is on the back of the periodic table. So you should see there that a zinc ion has a charge of +2. So on the right hand side, when zinc is part of zinc nitrate, you would write the formula as Zn2+. Again, the other way of doing it is by thinking of your formula of your zinc nitrate. Again, your formula is Zn, so there's just one zinc ion, and then you have two nitrate ions, NO3-. If you have two of those ions, the overall charge from your nitrate ions is -2. So your zinc ion must have a charge of +2 to cancel that out. So a couple of different ways that you can see the charges on your ions there, but essentially the charge on your iron ion is +2 and the charge in your zinc ion is +2 as well. So remember what you need to do. Write your two half equations, one for iron, one for zinc. Explain what's happening in each of those half equations, and then write your definition for a redox reaction. So if you need to go back to the example on the previous page, then please do, but have a go at writing this yourself. If it's not completely right, that's fine, but have a good go at it, and then I will go through it afterwards. So pause the video now, give that a go, and then I'll go through it. So I'm going to start with zinc, just because that will keep our answer in the same order as the previous example, but if you wrote the iron half equation first, that's absolutely fine. So let's have a look at what's happening to zinc. It's starting as an atom on the left hand side, so we write it as Zn with no charge, and it's forming zinc nitrate, and we've said that the zinc ion within that formula has a charge of 2+, so we write it as Zn2+ on the right hand side. So we're going from an atom to an ion. Which side do I need to add my electrons to? I need to add it to the side where the ion is, and that's to cancel out the positive charge to make sure the charges on both sides of my equation are the same. So I need to add my electrons to the right hand side. How many do I need to cancel out that 2+ charge? I need 2 electrons in total. Then we need to think, is this loss or gain of electrons? Remember, electrons on the right hand side means that electrons are being lost. Then we need to explain this half equation in words. So what has happened to our zinc? Zinc has lost 2 electrons. What does that mean? What is the loss of electrons? Then we need to think what is happening in terms of the iron. So we can see on the left hand side that iron is an ion with a charge of +2. And on the right hand side, iron is an atom with no charge. So let's write our half equation. We're starting on the left hand side with an iron ion with a charge of 2+. And we're forming on the right hand side an iron atom with no charge. Which side do my electrons need to go on this time? They need to go on the left to cancel out that positive charge. How many electrons do I need? I need 2 electrons to fully cancel out that 2+ charge. Then we need to explain this half equation in words. What has happened to my iron ion? Again, if you find it difficult to see whether this is gain or loss of electrons, remember to learn the rule that electrons on the left hand side is the gain of electrons. So we can see here that the iron ion has gained 2 electrons. That should be your first sentence. And then you need to go on and say that the gain of electrons is defined as reduction. And then finally finish off with your explanation of why this is a redox reaction. Well, it's a redox reaction because you have reduction and oxidation occurring simultaneously in the same reaction. So just simply state your definition of a redox reaction. So a redox reaction is reduction and oxidation occurring simultaneously in the same reaction. So just make sure that you're familiar with writing these types of explanations. And it's always the same structure. 2 half equations, 2 explanations, and the definition of a redox reaction. You'll get a little bit more practice in this style of question in the questions at the end of this topic. And just make sure you refer back to these 2 worked examples if you need. And finally, to finish off this section, we're just going to look at a few industrial examples of oxidation or reduction or redox reactions. These are reactions which take place industrially on a large scale. It's nothing new. Most of these reactions we've actually looked at already in this topic, but it's just because on your specification it specifically mentions that you need to link oxidation reduction and reduction reactions to industrial reactions that are studied in either this topic or in other topics across your specification. So we'll just fly through this really quickly. The first industrial reaction we'll look at is the extraction of aluminium. Again, we've already looked at this within this topic and we'll look at it in our electrochemistry topic. So we mentioned above that aluminium is extracted from its ore, aluminium oxide, by electrolysis. The oxygen is essentially removed. So you can see that it's reduction in the sense that it loses oxygen, but if we also look at it in terms of electrons, we start with an aluminium ion because it's part of aluminium oxide. Aluminium ions have a charge of 3+. That forms an aluminium atom which has no charge. How does it do that? Well, in terms of electrons, it needs to gain 3 electrons to cancel out that 3+ charge. So in terms of electrons, this is reduction because the aluminium ion has gained 3 electrons. And we would then go on and say that the gain of electrons is defined as reduction. So these explanations always have the same structure. What has happened in terms of electrons or hydrogen or oxygen, and then state whether that's oxidation or reduction. So the extraction of aluminium and industrial reaction is reduction because the aluminium ions gain electrons, 3 electrons each. We'll also look at something called the Haber process, in which nitrogen reacts with hydrogen to form ammonia, and that's then used in fertilizers and things like that. So this is a really important industrial process. We'll look at it in a couple of topics. And what we can see here is that nitrogen is forming NH3. So you can see that it has gained hydrogen. And then you need to think, is the gain of hydrogen oxidation or reduction? Go back to your summary if you need, but you should know by now that the gain of hydrogen is defined as reduction. So if you were asked, explain why the Haber process is a reduction reaction, you would say that nitrogen has gained hydrogen the gain of hydrogen is defined as reduction. Let's now look at an industrial example of a redox reaction. We're going to look at the extraction of iron. We've already looked at this in this topic, so we'll go through it really quickly, and we're going to study it a bit more closely later on as well. But let's look at it in terms of it being a redox reaction. So we can see from our equation, what we're trying to do here is extract iron from its ore, iron oxides. We're essentially trying to remove the oxygen from iron oxide. So you can see here we've got Fe2O3 and we're forming pure iron with no oxygen. So what has happened to the iron oxide? Well, we can see it has lost oxygen. How do we define the loss of oxygen? The loss of oxygen is reduction. And so we say that iron oxide has been reduced to iron. So it has undergone reduction. We describe that process as being reduced. So iron oxide has lost oxygen. Loss of oxygen is defined as reduction. Or we can think of it in terms of electrons. So we can see that it's iron 3 oxide. So that means that the iron ion as part of iron oxide has a charge of 3+. We're forming just simply iron atoms with no charge. How do we do that? How do we cancel out that 3+ charge on the iron ion? We need to gain 3 electrons. So we would say here that iron has gained 3 electrons, or the iron ion has gained 3 electrons. What is the gain of electrons defined as? Think of oil rig. The gain of electrons is reduction. So in two ways we can see that iron has been reduced. We can see that in terms of the fact that iron oxide has lost oxygen, but also the iron ions within the iron oxide have gained electrons, and that is also defined as reduction. So we could say this process is reduction, and that is the main purpose of this reaction, to extract the iron. But that's not the full story. We can see that we have what we call a reducing agent, the thing that reduces the iron oxide, and that's carbon monoxide. Carbon monoxide has the formula CO. It has just one oxygen, and that means essentially it has room for another oxygen, because we know carbon dioxide can be formed. So if carbon monoxide gains one more oxygen, then it will become carbon dioxide. So look at what is happening in this reaction in terms of carbon monoxide. It is gaining oxygen. And we know that the gain of oxygen is defined as oxidation. So while iron oxide is reduced to iron, carbon monoxide is being oxidized to carbon dioxide. Let's write that down below. I've just rewritten the equation so that you can see it on your screen as well. So we're focusing on our carbon monoxide and how it is gaining oxygen to become carbon dioxide. So we need to write in these gaps that as iron oxide is reduced to iron, carbon monoxide is oxidized to carbon dioxide. Why is that? Well, that's because carbon monoxide, as we can see from our equation, has gained oxygen, and the gain of oxygen is defined as oxidation. So we can see here that our iron oxide is reduced to iron, but our carbon monoxide is oxidized to carbon dioxide. So you can see that reduction and oxidation are occurring in the same reaction here, and so we can define this as a redox reaction. Why? Because redox is reduction and oxidation occurring simultaneously in the same reaction. So in that gap, just write your definition of a redox reaction. Redox is reduction and oxidation occurring simultaneously in the same reaction. So that finishes us off the first section of this topic and the main section of this topic, and this will be the biggest section. What I'd like you to do now is complete the questions on page 14 to 16 of this booklet. Completing all questions, there are 6 in total. I'd like you to do all your explanations in full, so no short explanations. And you can complete these in your blue book, or you can complete them on file paper if you want to keep your Year 12 content separate. Just a quick reminder, you have already done question 1, so that should be already done, so just continue on from question 2. So what I mean by explain in full is, say for example we looked at part 3 here. It says explain in terms of electrons why this is an oxidation reaction. Again, you want your 2-sentence structured answer there. So is magnesium losing or gaining electrons, and then your comment of the loss of electrons is defined as oxidation. So your explanation's in full. And then just flick over to page 15 with me. I just want to have a brief look at number 4. So number 4 is one of those more difficult examples. So we did 2 worked examples of this type on page 10 and 11. So if you want to write yourself a wee note, if you're struggling with this, see your examples on page 10 or 11. This is worth 5 marks. It says, I took this directly from an exam question. It says you may use ionic equations to help answer this question. That should really say you should. So you'll need to use half equations to answer this question. And just to remind you that sometimes they use that word ionic when really they should use half equation. So remember, you're splitting it up into what's happening in terms of each of your metals. It's very similar for question 5, but it's just split up into different parts, so it'll be a little bit easier for you. So question 5 is similar, but just split up. So just make sure for those 2 questions that you're explaining fully, you're splitting up into half equations and explaining them that way. And then don't forget, question 6 is on page 16, and that takes us to the end of this first part of this topic. In our next video, we will look at rusting and how we prevent rust, and we will look at the industrial extraction of iron in the blast furnace as well.